Hi everyone, welcome back. I'm Claudio Argentino, and in this video we are going to talk about sampling techniques for pore fluids, so water and gas trapped in the sediment. First of all, we have to collect sediment cores. In this short video we will see the gravity coring technique, which is the common technique used here at UIT. This is a gravity corer composed of weight on top and then a steel barrel which is going to collect the sediment. And this is how it looks like, the one we use. It's 6 meters long, so pretty long, and the diameter is 10 centimeters, the inner diameter. And you can see it, have a closer look here. And inside it hosts a plastic liner, so the sediment is eventually collected in the liner. And this is a core catcher. The core catcher is placed at the bottom of the gravity corer to avoid any sample loss. And you see it mounted here. So how does it work? The gravity corer penetrates the sediment and then it's pulled up and the sediment stays inside. Then we remove the core catcher, the liner, and we cut the liner into 1 meter section because it's easier to handle for further samplings. You see, for instance here, a pore water sampling. Another coring technique we commonly use is the multi-coring. The multi-corer is composed of a steel frame. You see the frame here, and it hosts up to 6 core liner, transparent liners, 70 centimeters in length and around 10 centimeters in diameter. And this is a picture taken when the multi-corer came back on deck with the sediment inside. So how does it work? The multi-corer is lowered into the water column and then it reaches the seafloor. Then the weight on top, which is this one here, pushes the corer into the sediment. Then we pull the multi-corer up again. The corer came up of the sediment and the whole structure came up, and we take it on deck. Whenever we have a possibility of having an ROV on board, a remote operated vehicle, we generally also conduct more habitat-specific samplings using these blade corers or push corer. So with the ROV arm, we push the blade core or the push core into the sediment. These are generally shorter, you see. With the blade core we get a slice of sediment with length of a maximum of 30 centimeters, more or less, and then it has a rectangular base. With the push core we can get longer core, up to half a meter length, and then the diameter of this push core here is around 8 centimeters. And you see we really have full control over the sampling area because we have a video mounted on the ROV that we can follow live from on board. So the first thing we do when the core are back on deck is collecting gas from the sediment, because the gas readily escape, so we don't want to lose it. We don't want to have any alteration from other atmosphere gases. So we get a slice of sediment, we put it into this jar, and then we seal the jar. We commonly also add some water and a bactericide in it to stop any microbial activity that can alter the composition of our gas. And then we store it upside down, so the gas, we are sure, is not going to escape from the lid, but it's going to be collected into the headspace. And this jar technique is used when we need to do some isotopic analysis. So we need a quite good enough amount of gas for this type of analysis. But often we just want to see how much methane is in the sediment. So we can use smaller vials, like this one here. So these vials contains 5 milliliters of sediment, and then again some bactericide. And then we seal it, and we store it upside down. The step after the gas collection is pore water collection, and we can do it in several different ways. The video here is showing the Rhizome sampling techniques. So we stick a filter into the sediment core, and then we attach a syringe. We keep the syringe wide open with a wooden stopper, and then we let it drain. So the water is eventually collected into this syringe, and it can take a few minutes if the sediment is highly permeable, but it can also take overnight if it's a very sticky sediment, low permeability sediment, or if it's highly consolidated. So actually the advantage of this technique is it's rather quick. We can do high resolution sampling, we can do every centimeter potentially. It's non-destructive, and there's no further filtering required because the Rhizome filters are already fine enough to get clean water in the syringe. As we said, it doesn't work out for highly consolidated sediment because the Rhizome technique is not efficient enough. The pressure is not strong enough to extract the water. And it doesn't work for carbonate-rich sediment if you are interested in carbonate geochemistry in your pore water. Another technique is known as a squeezing technique, generally employed during IODP cruises. Basically, we put a slide of sediment under a press. So we are squeezing the water out of the sediment. The water is collected into a syringe, and then we can do filtering and further processing. So the advantage is we get a large amount of water, and it works out pretty well also for highly consolidated sediment. For instance, if we have this long drilling project, we are getting sediment from kilometers beneath the seafloor, so the sediment is very consolidated. This is a technique that can help you get water out of the sediment. These advantages, it's pretty time consuming. You have to get a slice of sediment, put it in the press, and then clean the instrument. It's pretty time consuming. You are destructing your sediment sample. Specifically, you are losing information about the sedimentary structures. It's a low resolution sampling, you cannot do every centimeter. And it requires heavy machinery. Centrifugation, this technique can be easily done on board. Generally, if you are interested in nutrient analysis, this is something you can do. Very intuitively, we placed a volume of sediment into these tubes, and we also add some immiscible liquid to separate the pore water from the sediment. So we start our centrifuge, the water is escaping the sediment and migrating on top of everything. And then we simply pipette it out of the centrifugation vial, and we put it in other container depending on the analysis we're interested in. So the advantage is we can do high resolution sampling. Disadvantage is pretty time consuming. It's considered destructive because, again, we are losing some sedimentological information about structures. And it requires generally a further step of filtering. We want to remove particulate organic carbon, that can have migrated with the water, and we require some sort of heavy machine. After extracting the pore water, next step is splitting into different aliquot for different type of analysis. Then we do some fixation. We want to preserve our sample. If we are conducting analysis onshore after weeks or months, we need to be sure our geochemical composition of the sample is intact, is unaltered. So for trace metal analysis, for instance, we add some nitric acid to keep the metals into solution. For dissolved inorganic carbon, DIC, one way of preserving the sample is adding mercury chloride, because it kills all the microorganisms that can potentially affect your DIC geochemistry. After the sample fixation, we generally store the samples in a fridge or in a freezer until onshore analysis.